The position, velocity and acceleration of a particle that's moving along a curve can be expressed in polar coordinates. So we have the origin, or the pole, and the polar axes along the radial vector to the position of the particle. And the position of the particle in polar coordinates is r, being the magnitude of the position vector, and theta, which is measured anti-clockwise from the horizontal axis. And these two unit vectors describe the motion in the radial direction and the theta direction. So these are orthogonal unit vectors, or orthonormal vectors. So we can express these unit vectors in the Cartesian coordinate system as having a horizontal component, where this angle is theta. So we have cosine theta in the I direction, plus a vertical component, which is sine theta in the j direction. And the theta unit vector can be expressed in a similar way, where this angle here is equal to theta. So we have theta hat is equal to the component in the horizontal direction, which is minus sine theta in the I direction, and the vertical component is cosine theta in the j direction. Now the position of the particle from the pole is defined by the radial vector, which is the magnitude of the radial vector by the unit vector in the radial direction. And differentiating this, we get the velocity. So using the product rule, we get the derivative of r with respect to t, which we'll write in shorthand notation as r dot, by r hat plus r by the derivative of the unit vector with respect to time t. So as the particle moves along the curve, these unit vectors change direction with respect to time. So unlike the Cartesian coordinate system, where the I hat and j hat unit vectors are constant. So we can find dr dt by using the chain rule. So that's equal to dr hat d theta by d theta dt. And in shorthand notation, this is the angular velocity, which we'll write as theta dot, being the first derivative of theta with respect to time. So differentiating r hat with respect to t, we get dr d theta, which is minus sine theta in the I direction, plus cosine theta in the j direction, multiplied by d theta dt, which is theta dot. And this term in the brackets is the unit vector in the theta direction. So that's equal to theta dot by theta hat. And therefore, we can replace this term with theta dot by theta hat. And now we can differentiate again to find the acceleration. So using the product rule and differentiating the first term, we get the second derivative of r with respect to time by r hat plus r dot by dr hat dt, which we found to be theta dot by theta hat. And differentiating the next term, we get r dot by theta dot by theta hat plus r by the second derivative of theta with respect to time by theta hat, and plus r by theta dot by d theta hat dt. So similarly, by the chain rule, we can find d theta hat dt by first differentiating theta hat with respect to theta. So we get minus cosine theta in the I direction, minus sine theta in the j direction multiplied by d theta dt. So the term in the brackets is equal to minus r hat. So therefore, we can replace this term. So we get minus r theta dot squared in the radial direction. And now we can group the acceleration terms in the radial and theta direction. So we get the acceleration is r dot dot minus r by theta dot squared in the radial direction plus r by theta dot dot plus 2r dot theta dot in the theta direction. And these are the vectors describing the motion of a particle in the plane in polar coordinates. We can extend the motion of a particle in a plane, which we describe using the polar coordinates r and theta, into the motion of the particle in space using an additional z coordinate. So here we're extending the polar coordinates to cylindrical polar coordinates. And the radial vector from the pole to the particle is obtained by vector addition. So we have a radial component, which we had in polar coordinates, plus a vertical component having a magnitude of z in the k direction. And now if we differentiate r with respect to time, we get the velocity, where the derivative of the first term is exactly the same, plus the derivative of the second term, which is the derivative of z with respect to time, being the velocity in a z direction, by k hat. So note that k hat is constant and does not change with time. And then differentiating again, the derivatives of these terms give the exact same components for the acceleration in the radial and theta directions, and we add the derivative of the z term, which is the acceleration in the z direction, or the second derivative of z with respect to time, in the z direction, where k is constant. We can use polar coordinates to describe the motion of the planets around a star in a solar system. So here we take the pole at the star, and we draw the radial vector to the planet that's orbiting the star. So the star exerts a gravitational attraction on the planet, which is a gravitational force. So we treat the planet and the star like a particle, where the force is acting through the center of mass. And similarly, by Newton's third law, the planet exerts an equal and opposite attractive force on the star. And this gravitational force is equal to minus of the universal gravitational constant by the mass of the star by the mass of the planet on the squared magnitude of the radial vector between them. And this acts in the r hat direction. So in other words, r hat is taken in this direction from the star, and therefore the gravitational force acting on the planet acts in a negative r hat direction. And note that r hat is the unit vector in the direction of r. So we have r on the magnitude of r. So if we apply Newton's second law to the planet, then this force is the mass of the planet by the acceleration of the planet in the radial direction. So note that the acceleration acts in the same direction as the net force, and therefore there's no acceleration in the theta direction. So here we can see the force points in the opposite direction to the r hat unit vector. And in polar coordinates, we have a perpendicular theta hat direction. So the only acceleration is in the radial direction. So if we simplify this equation, we get minus g by ms on the squared magnitude of r in the r hat direction. So the mass of the planet cancels. So no matter where the planet is in the orbit, it accelerates towards the star's center of mass at all times. So given r hat is the radial vector on its magnitude, then we can see that the acceleration is a scalar multiple of the radial vector. So in other words, the two vectors are parallel, and therefore the cross product between the acceleration and position vectors gives the zero vector. So noting the velocity vector is tangential to the curve, we can show that the motion of the planet is in the plane by taking the derivative of the cross product between the position vector and velocity vector with respect to time. So using the product rule, that gives the velocity cross the velocity plus the cross product between the position vector and the acceleration vector. And note that the only acceleration is acting in a radial direction. So the acceleration is equal to AR. And the cross product between parallel vectors is 0. And as we saw, the acceleration vector is also parallel to the position vector. So this evaluates to the 0 vector. So given the derivative of this cross product is 0, then the cross product between the position vector and the velocity vector is a constant vector. So this cross product does not change with time. So the resultant vector points out of the plane of the orbit, or out of the screen, and therefore the position and velocity vectors lie in the same plane, perpendicular to this constant resultant vector. And consequently, given that the orbital angular momentum of the planet is defined as the cross product between the position vector and the linear momentum of the planet, being the mass by the velocity, and this is a vector quantity, so that means that it's equal to the mass by a constant vector. So therefore the angular momentum of the planet is also constant, no matter what position it is in the orbit. And we'll use these ideas to derive Kepler's laws that describe the orbit in more detail. Kepler's first law states that the path of a planet orbiting a star has an elliptical path with the star at one focus. And this can be derived by applying Newton's second law to this planet. So recall that we derived this already, where the only force acting on the planet was a gravitational force. And applying Newton's second law, we came up with the acceleration in the radial direction was equal to the negative of the universal gravitational constant by the mass of the star on the squared magnitude of the radial vector from the star to the planet. So this is in the radial direction. So that will be this direction in polar coordinates, and the theta direction is perpendicular to the radial direction. Now recall in polar coordinates, the radial component of the acceleration is the second derivative of r with respect to time minus r by the square of the angular velocity. So therefore, given that r hat appears on both sides, we can rewrite this equation in scalar form. So we have the component of ar as a second derivative of r with respect to time, minus r by the square of the angular velocity. And using the magnitude of the angular momentum, which we showed is constant throughout the motion, and noting the velocity vector is tangent to the path, and the angular momentum is the magnitude of the radial vector by the magnitude of the momentum vector sine theta. So that's the angle between r and the velocity vector. Then v sine theta is the component of the velocity vector in the theta direction, which is perpendicular to r. So therefore, we can write this as r by m by the component of velocity in the theta direction. And recall the component of the velocity in the theta direction was r by the angular velocity. So the magnitude of angular momentum can be written as m by r squared by the angular velocity. And rearranging this gives the angular velocity in terms of the angular momentum. And one way we can solve this differential equation is by substitution. So we can set r equal to our dummy variable, and then differentiating r with respect to time t, we can differentiate first with respect to u, and then differentiate u with respect to theta, and differentiate theta with respect to time t. So that's applying the chain rule. So dr du is minus u to the minus 2 by du d theta by the angular velocity, and substituting for r in the angular velocity, we have ln m by u squared. So substituting for the angular velocity, u to the minus 2 by u squared cancels, and we get minus ln m by du d theta. And if we differentiate again, we get the second derivative of r with respect to time. So using the chain rule, we get minus ln m, and then by the chain rule, we first differentiate with respect to theta, and multiply by d theta dt. And now if we substitute for theta dot, we get minus L squared on M squared by U squared by the second derivative of U with respect to theta. So therefore, if you substitute for theta dot and the second derivative into this equation, we get minus L squared on M squared by U squared by the second derivative of U with respect to theta minus R, which is 1 on U, by theta dot squared, which is L squared on M squared by U to the 4. Let's make a bit of space. And on the right hand side, we have minus G by the mass of the star by the squared magnitude of R, where R is the magnitude in shorthand notation. So therefore, we have U squared. And now if we divide through by negative 1 and cancel U squared, So here we have u cubed on u squared, which gives u, and then multiply through by m squared and divide through by l squared. We get the second derivative of u with respect to theta plus u is equal to g by ms by the mass of the planet squared on the square of the angular momentum. So this is a familiar second order differential equation with constant coefficients in a similar form obtained for simple harmonic motion. So the solution is u of theta is equal to a constant by the cosine of theta plus the constant term on the right hand side, which is g by ms by m squared on l squared. And now we can substitute back for r. So u is equal to 1 on r. And therefore, we can write r as the reciprocal of this term on the right hand side. And now we want to get this in the form of the equation of an ellipse. So what we can do is factor out this constant. So we get 1 over g by ms by m squared on l squared. Let's multiply by 1 plus the eccentricity of an ellipse by cosine theta. So recall that the equation of an ellipse was equal to the length of the semi-major axis by 1 minus the square of the eccentricity on 1 plus e cosine theta. And that's the form we're looking for. And by observation, we see the eccentricity is equal to a, being a constant, by l squared on g by ms by m squared. So this term multiplied by e gives back a. So firstly, we have the closest distance from the star to the planet being perihelion. So we'll call this the radial distance, the perihelion. And the furthest distance is called aphelion. So we'll take this as Ra. So this point in the orbit is obtained when theta is equal to 0. And aphelion is obtained when theta is equal to pi. So when theta is equal to 0, we get the closest point in the orbit being perihelion, and that's equal to 1 over this term, which is gms by m squared on l squared by 1 plus the eccentricity. So if we multiply through by 1 plus e, we get this reciprocal as equal to the radial distance to perihelion by 1 plus e. So therefore this expression can be written as r of theta is equal to the distance to perihelion by 1 plus e on 1 plus e cosine theta. And from this expression, when theta equals 0, we also have the distance to perihelion as the reciprocal of the constant a by cosine 0 plus this constant. So if we solve for a, we just multiply through by the term in the denominator and divide through by rp and subtract this constant from both sides. And therefore, if we take this expression and substitute for the eccentricity, so let's just make a bit of space here, then we get E is the reciprocal of RP multiplied by L squared by G by MS by M squared minus 1. And noting the angular momentum at perihelion is the radial distance to perihelion from the Sun by the mass by the velocity, then we get RP squared by M squared by VP squared. And therefore the mass of the planet cancels, and RP cancels with RP. And therefore we can write the eccentricity of the orbit in terms of the radial distance to perihelion by the squared magnitude of the velocity on the universal gravitational constant by the mass of the Sun minus 1. So let's copy these equations and observe our orbit. Now when theta is equal to pi, we get the distance to aphelion, which is the distance to perihelion, by 1 plus E on 1 minus E. And noting the length of the major axis of the orbit is 2A, which is equal to the distance to aphelion plus the distance to perihelion, which we can multiply by 1 minus E on 1 minus E. So that gives 2A by 1 minus E is equal to 2RP. So therefore, given RP is the length of the semi-major axes by 1 minus the eccentricity, then we can write this equation as the length of the semi-major axes by 1 plus E by 1 minus E, which is 1 minus E squared, over 1 plus E cosine theta. So that proves that our orbit is elliptical. So note that A is the distance to perihelion plus aphelion on 2. But in general, we'll use this form as it's more convenient. Kepler's second law states that the radial vector from the Sun to a planet sweeps out equal areas in equal times. So recall that we showed that the orbit was elliptical and planar. So the planar condition was that the cross product between a position and velocity vector was constant. And now if we substitute for these vectors, we have the magnitude of the radial vector in the radial direction, and we take the cross product with the velocity vector, which had a radial component plus a component in the theta direction, which was r theta dot by theta hat. So note that the velocity vector is tangent to the path. So it has a component in the radial direction and a component in the theta direction. So evaluating the cross product, we get r by r dot by the cross product between a radial unit vector and itself plus r by r theta dot Well, the cross product between r hat and theta hat. So this term is 0 because the radial vector is parallel to itself. And this term gives r squared theta dot in a direction pointing out of the screen. So this here is equal to a constant vector. So to find the constant vector, we'll just take the condition where the planet is at perihelion, being the closest distance to the Sun, at time 0. So at perihelion, the velocity vector, being tangent to the path, only acts in the theta direction. So therefore r perihelion by the angular velocity is equal to the velocity. So taking this condition, we can write the constant as r perihelion by r theta dot, which is the speed at perihelion in the k direction. And recall the differential area of a polar curve was equal to 1/2 by the base of the triangle, which was r by d theta, by the height of the triangle, which is r. So if we integrate this, we get the area enclosed by the curve between two angles, being theta A and theta B. So if we do a change of variables, then we're integrating with respect to time instead. And if you apply the fundamental theorem of calculus, while taking the time at B to be some time t, we get dA dt is 1/2 by r squared theta dot. And given that r squared theta dot is constant, and thereby equal to the distance from the Sun to perihelion by the speed at perihelion, so the change in area with respect to time is constant, and therefore the area is constant with time. So two areas swept by two radial vectors over the same time interval are equal. So that gives Kepler's second law. And recall the angular momentum at perihelion was Rp by the mass of the planet by the speed at perihelion. So if we substitute for Rp Vp, we get 2m by dA dt. So the angular momentum is also constant throughout the planet's orbit. So in other words, if we take a radial vector to aphelion, then the planet travels at a slower speed because the distance to the Sun is larger, such that the angular momentum remains constant. So this is the conservation of angular momentum. Kepler's third law states that the period of the orbit, which is the time taken for the planet to go around the Sun once, is related to the orbit's semi-major axis A as t squared on A cubed is equal to 4 pi squared by the gravitational constant by the mass of the Sun. So this ratio is constant for every planet in the given solar system. Now recall that we found that the rate of change of area swept by the radial vector to the planet with respect to time was equal to a constant. So we chose the initial condition to be the position of the planet at perihelion. So we had the distance to perihelion by the speed at perihelion. And if we separate the variables and integrate both sides from time 0 to the period of the orbit, we get the total area of the ellipse being related to the period. So we have 1/2 by t by rp by vp. And we know the area of an ellipse is pi by the length of the semi-major axis by that of the semi-minor axis. So we can flip this equation around for the period of the orbit. So we have 2 pi by AB over RP by VP. And furthermore, we've seen for the conic sections that the length of the semi-minor axis is related to that of the semi-major axis. So it's equal to A by the square root of 1 minus the square of the eccentricity. Now what we want to do is get G multiplied by the mass of the Sun into this equation. So recall when we derived Kepler's first law, we had the eccentricity of the orbit was the distance to perihelion by the speed at perihelion squared on the universal gravitational constant by the mass of the Sun minus 1. And we also had a relationship between the major axes and the radial distance to perihelion. So if we substitute for the eccentricity, we get 2a is 2rp on 1 minus negative 1, which is 2, minus rp vp squared on gms. So we can write this as 2 by g by ms on g by ms. And therefore this equation simplifies to 2rp by gms over 2gms minus rp by vp squared. Now let's make a bit of space over here. So if we square both sides of this equation, we get the square of the period as 4 pi squared by a to the 4 on rp squared by vp squared by 1 minus the square of the eccentricity. Now let's remove this equation and make a bit of space. So we'll just keep this relationship and the eccentricity. And now we can substitute for the eccentricity. So we have t squared is this term, and that's multiplied by 1 minus the square of the eccentricity, which is rp vp squared on gms minus 1 all squared. And now expanding the bracket, we have 1 minus 1, which is 0, minus minus 2 by rp by vp squared on g by ms, and minus rp squared by vp to the 4 on gms squared. And that's multiplied by this constant over here. And that's equal to t squared. And now if we multiply the first term by gms on gms, and we'll take this term again and factor out rp by vp squared and gms squared in the denominator, then what we get is 2 by g by ms minus rp by vp squared. So if we do some simplifications, rp cancels and vp squared cancels. And therefore the square of the period is 4 pi squared by a to the 4 on RP by GMS squared, and in the brackets we have this term, and therefore we can replace this term as 2RP by GMS on 2A. And now doing some cancellations, RP cancels with RP, GMS cancels with this one, and one of these A's cancels with this one, so we get A cubed, and the 2's cancel. So dividing through by A cubed, we get T squared on A cubed is 4 pi squared on the gravitational constant by the mass of the Sun. And this here is Kepler's third law. Given the following constants, calculate the eccentricity of the orbit, which were derived using Kepler's first law as the distance from the Sun to perihelion by the square of the speed at perihelion on a universal gravitational constant by the mass of the Sun minus 1. And the distance from the center of the orbit to the Sun is the distance to the focus, which was equal to the length of the semi-major axes by the eccentricity of the orbit. And we can obtain a period of the orbit using Kepler's third law, which was a period squared on the length of the semi-major axes cubed is equal to 4 pi squared on the universal gravitational constant by the mass of the Sun. So if you make those substitutions and make the units consistent, so we'll convert the distance to perihelion into meters, and the speed at perihelion in kilometers per second can be converted to meters per second by multiplying by 10 cubed. So now the units are consistent. And if we substitute those numbers, we get the eccentricity of the orbit, so that gives 0.01663. And recall Kepler's first law was r as a function of theta, giving the radial position of the planet in the orbit was equal to the distance to perihelion by 1 plus the eccentricity of the orbit over 1 plus e cosine theta. So to find the distance to the focus, which is the distance from the center of the orbit to the Sun, we need the length of the semi-major axes, which is the distance to perihelion plus the distance to aphelion on 2. And we can find the distance to aphelion by substituting for the eccentricity of the orbit, and theta is equal to pi, as well as the distance to perihelion, which is given. So this gives the distance to aphelion as 152,073,294 kilometers. And now we can find the length of the semi-major axes by substituting for RP. So that gives 149,585,684 kilometers. And if we substitute this into this equation, and also substitute the eccentricity of the orbit, we get 2,487,610 kilometers. So given this very small value of eccentricity, the orbit is almost circular, and if this is the center of the ellipse, the Sun at the focus is very close to the center of the ellipse. So the orbit of the planet around the Sun is almost circular. So we can see the distance to the focus is a lot smaller than the length of the semi-major axes of the ellipse. And the period of the orbit, using this equation, can be obtained by substituting for A, the universal gravitational constant, and the mass of the Sun. And note that you need to convert A into meters to have consistent units. So that gives 31,549,658 seconds, which I'll let you convert to days as an exercise, which gives around 365.16 days. So as we know, the Earth takes 365 days, or 1 year, to go around the Sun once. And noting this error, so had we included more decimal places, this is closer to 365.25 days, and 1 year is 365 days. So that's why a leap year, which occurs every 4 years, is 366 days, to account for this error, as it doesn't exactly take 365 days for the Earth to orbit the Sun. Find the velocity and acceleration vectors given the position vector. So the velocity is the derivative of r, being the position vector, with respect to time. And given r is a function of theta, we'll use the chain rule, first differentiating with respect to theta, and multiplying by d theta dt, being the angular velocity. So dr d theta is minus a cosine theta by d theta dt, which is 2. And we can obtain the acceleration by differentiating the velocity with respect to time. So again, applying the chain rule, we have dv d theta by d theta dt. So that gives 2a sine theta, and multiplied by d theta dt, we get 4a sine theta. Show that the speed of a planet in a circular orbit is constant. So recall, in an elliptical orbit, we had the cross product between a radial vector from the Sun, which is at one focus, and the velocity vector, which is tangent to the curve, is constant. So the orbit is in the plane. Now if we resolve the velocity vector in the radial direction, and it also has a component in the theta direction, then the cross product between r and v is the magnitude of r by the magnitude of v by sine of the angle between them, where this is the angle alpha. So as we can see, v sine alpha gives the magnitude of the component in the theta direction. So we can write this as r by v theta, and the magnitude of the cross product is equal to the magnitude of the constant vector out of the plane, being the resultant of the cross product. And for a circular orbit, the magnitude of the radial vector is constant. So we get the magnitude of velocity in the theta direction, or the speed, is c on r, which is thereby constant. So noting for a circular orbit, there's no velocity in the radial direction. The velocity in the theta direction is always tangent to the path.